5.2 is called Frequency Tables, Histograms, and Frequency Polygons. So, we're going to be learning about these three different types of frequency distributions. A frequency distribution is a set of intervals, a table or graph, usually of equal width, into which raw data is organized. Each interval is associated with a frequency that indicates the number of measurements in this interval. So if we look at learn about the math on page 213, it says that flooding is a regular occurrence in the Red River Basin. During the second half of the 20th century, there have been 9 notable floods, 4 of which have been severe, occurring in 1950, 1979, 1996, and 1997. The flood that occurred in 1997 is known as the flood of the century in Manitoba and North Dakota. The following data represents the flow rates of the Red River from 1950 to 1999, as recorded at the Redwood Bridge in Winnipeg, Manitoba. So here we have our data. We have the years the flood occurred and the flow rate. So here are my 4 floods. The question says, how can you approximate the water flow rate that is associated with serious flooding in Winnipeg? So we're going to be creating the different types of frequency distributions. So let's look at Francine's solution. She's creating a frequency distribution table. So in order to create a frequency distribution table, what we do is we have to find our range. And we do that by taking our highest flow rate and subtracting our lowest flow rate from it. So that gives us 4428. Now usually frequency distribution tables have between 5 and 12 intervals. So here Francine chose to do 10 intervals because 4,428 divided by 10 is equal to an interval that's pretty close to a nice round number, 500. So then, if the interval width is 500, the intervals will end at 500, 1,000, 1,500, 2,000, 2,500, 3,000, 3,500, 4,000, 4,500, and 5,000. So all we need to do is we need to count the flow rates that are between 0 and 500. So here, Francine counted 6. So then she tallied 1, 2, 3, 4, 5, 6. And then she wrote it in numbers as 6. And she continued to do that until she was finished her graph. Sorry, her table. Then she analyzed her table. She says, well, we had 4 major floods, so we had 4 severe. So she said that the severe floods occur after we have a flow rate of 3,000 meters cubed per second. Because here, if you see, 3 plus 1 equals 4. And then she said that she predicted the water flow rates that resulted in serious flooding were greater than 2,000. And she can check her prediction by comparing the years that had flow rates from 2,000 to 3,000 with the historical records of flooding. So that is how Francine approached this question. Tasha decided to approach this question a little differently. She created a frequency distribution called a histogram, which looks a lot like a bar graph but isn't a bar graph. So how she did that, she made herself a frequency distribution table and said that, well, she used an interval width of 450 instead of 500. And then she drew her histogram. Now, in order to draw a histogram, we need to determine 2 scales, our y scale and our x scale. Our x scale comes directly from our interval. Our y scale, she said the number of years that went up by 14. Okay, so she said that we had 150 to 600 11 times, so she drew her bar like this. She had 600 to 1,059 times, so she found 9. Notice that the bars in a histogram touch, unlike the bars in a bar graph. So then, she says, in general, with the exception of the interval 1500 to 1950, as the maximum flow rate increases, the number of data points in each interval decreases. So here we have lots of data points, whereas here we have very few. There were 9 floods, so based on this histogram, the flow rate was greater than 1950 meters cubed per second in only 12 years. These 12 years must include the flood years. I predict that floods occur when the flow rate is greater than 1950 meters cubed per second. Monique decided to use a frequency distribution called a frequency polygon. So what we have to do to make a frequency polygon is we have to still make our frequency distribution table. But the only difference is that we have to calculate the midpoint of our intervals. To do this, we add 150 to 600 and then divide it by 2, which gives us 375. And we continue doing this all the way down in order to calculate our midpoints. Then we have to create our graph. So our x-axis comes from the midpoints that we've found. Our y-axis, again, is our number of years. That goes up by 2. So Monique found that for our midpoint 375, we had 11 years. So what we do is we go up from 375 to 11 and plot our point. For the midpoint 825, she found that we had 9 years. So we go up 2, 4, 6, 8, 9, and we plot our point. And we continue doing this in order to create our frequency polygon. Generally, when we are making a frequency polygon, we have to make sure to connect the ends to our graph. But if you notice, all our frequency polygon really is the midpoints of our histogram connected together. So we take the midpoint of this bar, and this one, this one, this one, this one, this one, and this one, and we connect them together. This gives us the same shape of the frequency polygon as we got here. And to answer our question, Monique says there were 6 years where the flow rate was around 2625, 3075, or 4425 meters cubed per second. These must have been the flood years. The other 3 floods should have occurred when the flow rate was around 2175 meters cubed per second, so around here. According to her frequency polygon, there were flows around that midpoint in 6 years. So here we have 6. Assuming that the flow rate in the 3 of those years was 2175 meters cubed per second or greater, floods should occur when the flow rate is 2175 meters cubed per second or greater. If you look at example 2 on page 218, it says, the magnitude of an earthquake is measured using the Richter scale. Examine the histograms for the frequency of earthquake magnitudes in Canada from 2005 to 2009. Which of these years could have had the most damage from earthquakes? So we need to understand a little bit about the Richter scale. So it says that from 4.0 to 4.9, it's felt by nearly everyone, and there's movement of unstable objects. From 5.0 to 5.9, it's felt by all, and there's considerable damage to weak buildings. From 6.0 to 6.9, it's difficult to stand, and there's partial collapse of ordinary buildings. And from 7.0 to 7.9, there's loss of life and destruction. More than 7.9 is widespread loss of life and destruction. Okay, so if we go back up and we look at these, Biljana's solution is to use a frequency table. So she said that 2005 had the most earthquakes in any one category. there was 20 earthquakes with a magnitude from 3.0 to 3.9. So she says, at first glance, it seemed like 2005 was the worst year because it has the highest bar. However, an earthquake of a magnitude 3 does not cause much damage. So then she knew that some minor damage would occur if the magnitude is from 4.0 to 4.9. So she decided to examine the frequency of these earthquakes for 2005 to 2009. So what she did was she created a table. So 4 of the years had 3 earthquakes with magnitudes from 5.0 to 5.9, while 2008 had 5 earthquakes with these magnitudes. So she said that only 2008 and 2009 had earthquakes with magnitudes from 6.0 to 6.9, using her table. She decided to examine these years more carefully. She created a table for earthquakes from 4.0 to 4.9 on the Richter scale for these years. So she found that in 2008, 16 earthquakes occurred. In 2009, 7 earthquakes occurred with the same magnitude, 4.0 to 4.9. In 2008, 5 earthquakes occurred with 5.0 to 5.9, and in 2009, 3 earthquakes occurred with 5.0 to 5.9. So if you can see, 2008 has the higher number in all 3 columns. And this means that 2008 could have had the most damage from earthquakes. Miguel decided to use frequency polygons. So he said that in both 2008 and 2009 had the strongest earthquakes, registering from 6.0 to 6.9 on the Richter scale. So he looked at these histograms, which he plotted on the same graph. So the number of earthquakes in the 3 highest intervals was greater in 2008. So our 3 highest intervals were here, here, and here. And that's where our damage occurs. So he said that 2008 could have had the most damage from earthquakes.